Assalamualaikum warahmatullahi taala wabarakatuh. I'm going to talk about the lab test. First, we have to see let's take a look at the question which we have been given that the plant transfer function is equal to 10 over s plus 2 product with s plus 10. So we have to design a lag controller to improve the system response. So this is the specification, which is the peak time is less than 0.5 seconds and the steady state error is less than 5%. Also the percentage of overshoot less than 10%. So let's see with the first step. Let's start with the first step, which is we find the desired closed loop pulse. By using the formula, peak time is equal to pi over omega t and alpha is equal to omega t times with damping factor over 1 plus 1 minus square power of the damping factor, square root of both. We can find the peak time. We set the omega t is equal to 7, hence we can get the peak time 0.545 seconds. Then damping factor we set to 0.7 and can get the percentage of overshoot equal to 4.6%, which is both meet our specific requirement. So our desired pole is 6.9 plus minus J5. So let's move to the next step. We have from the notes where that lag controller have been given the formula GCS equal to KC S plus A over S plus B. So the step is we have to find that B is less than A and more than 0. So we set the 0 to the small value of B equal to 0.1 and A equal to 2. Why? So we can get the cancellation of the smaller pole of the plant. So from the root locus, let's open the Matlab. We can find from here that the breakaway point is equal to somewhere point at the negative 5.73. So the best closed loop pole is negative 5.73 J5. So we move to the next step, which is to find the Kc. So Kc is equal to 1 over the magnitude, which is the reciprocal of the GCGPS. And we substitute the S is with our closed loop poles location we have find just now. So by using this formula and then we substitute, we find that the Kc is equal to 7.37. So now we have the complete formula, complete plan to put into the transfer function. Now we open the Matlab and by here right now you can see that I have already put our transfer function 7.37 s plus 2 and s plus over s plus 0.1. The G we have been given in the question. Now let's say the response. So first we can see the response here for the peak time. Peak time 0.447 seconds and the percentage of overshoot is 10.4%. Meanwhile, the steady state error here is 0.987, which makes us the difference of the steady state error is 0.013, which is 1.3%. So peak time and the steady state error meet the specific requirement, but the percentage, however, is not meet our requirement, which is to be less than 10.4%. So I can change the value of gain. From here, in this case, I have choose because our design is not meet the specific requirement. So I have changed the design to 7, the gain KC to 7.5. Note that let's not focus on the compensator editor here, but focus on this preview here, 7.15. So when I substitute the original gain with 7.15, the new peak time is 0.45 second and the percentage of overshoot here is 9.88% with the steady state error is equal to 0.986, which bring us to the 1.4% steady state error. Now, all of these requirements, all of these response have meet our specific requirement. Hence, this controller is successful to meet the specific requirement from the question. So the next question is the phase margin and the gain margin. We can see from the board editor of the plot here, the gain margin is equal to infinity, which make the system will never be unstable, and the phase margin is 59.5 degree. That's all. Thank you.